If we consider the earthquake engineering design limit states that are typically associated with performance-based earthquake engineering, we see that the structural collapse limit state is the most severe. Operational, life safety, and structural stability are also shown on the slide and are commonly used to describe the less severe limit states preceding collapse. Moving on to our discussion of collapse behavior, the focus of the video will be to demonstrate ratcheting type collapse. Ratcheting collapse commonly occurs in more ductile structures associated with particular ground motions. As you'll see shortly, the structure will almost appear to walk towards collapse during the earthquake. On the other hand, non-ratcheting type collapse could occur with large pulse type ground motions or even with non-ductile structures. This slide shows a single degree of freedom structure with ratcheting type collapse after being subjected to the Chi earthquake scaled by a factor of 2.2. When we talk about collapse with ratcheting, what do we really mean? Well, if we look at this figure, we notice that up to approximately 50 seconds, the structure cycles about its undeformed configuration, or at least has relatively small residual deformations. Then the structure experiences a very large inelastic response at this first plateau, until a second pulse increases the lateral deformation. Finally, the structure deforms even more prior to collapse with a noticeable third segment, until final collapse at approximately 80 seconds. If we look at this behavior with a forced displacement hysteresis, the cycles prior to the large lateral movements have a relatively small residual deformation. Then the structure begins ratcheting with segments 1, 2, and 3 corresponding to the previous displacement time history. Collapse is marked by a minimal lateral strength capacity. Experimentally, ratcheting collapse can be demonstrated with the following single degree of freedom structure. Note that the structure has already yielded from a prior ground motion, and therefore has some residual deformations already. Nonetheless, it properly demonstrates ratcheting type collapse. Notice the discernible segments of lateral deformation, similar to those shown on the previous slides. Contrast this ratcheting type behavior with collapse due to a ground motion with a strong pulse. Shown on this slide is the displacement time history of the same single degree of freedom structure used to create ratcheting collapse shown before, only here it is subjected to the Loma Prieta earthquake scaled by a factor of 1.3. This is an example of non-ratcheting collapse as the structure experiences only 2 to 3 cycles prior to collapse from the large ground motion pulse from Loma Prieta. The forced displacement hysteresis shows a predictable behavior as the structure collapses virtually monotonically. Experimentally, non-ratcheting collapse is shown here with a non-ductile reinforced concrete structure tested on the E-defense shake table in Japan. Notice the immediate failure after the large ground motion pulse. While this behavior could be attributed more to the non-ductile nature of the structure rather than the ground motion itself, it is a nice visual demonstration of non-ratcheting collapse. Ratcheting behavior can be distinguished from non-ratcheting behavior by examining the displacement time history and forced displacement hysteresis. It is interesting that certain ground motions can lead to one type of response and not the other. Most notably, large pulse earthquakes may cause non-ratcheting collapse. Structure type and ductility will also contribute to the collapse response during an earthquake, as demonstrated with the E-defense shake table test of the non-ductile reinforced concrete structure.